Hi guys, welcome to today's lesson. So today we're going to be looking at some revision of rational exponents, right? But before we do that, we need to actually look at exactly what are we talking about when we talk about the concept of an exponent, right? Because that's where all of this starts from. And that's going to go to the laws of exponents, the definitions and the equations, and then we'll look at exactly how do we then, one, simplify them, two, how do we solve them as well, because remember, simplifying and solving are two different things. But for now, let's just jump right into it and see exactly what we have to do today. So, the first question that I want to ask you is, why do we write numbers and algebraic expressions as exponents, right? Exactly what are we trying to achieve when we take numbers and algebraic expressions and write them as exponents? But before that, we need to answer the question, what is an exponent? Our concept map is we're going to look at laws of exponents. We're going to look at some integers because exponents have to do with some integers. We're going to look at the definitions that are inside the exponents, equations, some surds, and rational numbers. So the key words for this lesson will be exponent and surd. Now, firstly, an exponent refers to the number of times a number, and this number, we call it a base, is multiplied by itself. So this is written in the form of a to the exponent of n, and this is an example of a general form of what an exponent is about, where the a is the base of the exponent and the n will be the exponent itself. So for example, let's say I have 2 to the exponent of 3. The 2 will then be my base, and the 3 will be how many times I'm going to multiply the base by itself. So since it's 3, it means I'm going to multiply it by itself 3 times. So that will be 2 multiplied by 2 multiplied by 2. So that's 1, 2, 3 times. It is multiplied by itself. Please don't think that I'm saying it's 2 multiplied by 3. No, it's 2 multiplied by itself 3 times. That's what an exponent is about, because we just said now the definition is how many times the base is multiplied by itself. So we have what we call the laws of exponents. With the laws of exponents is we normally use letters, variables that is, to show the laws of exponents. A to the exponent of m multiplied by a to the exponent of n will be the same as a to the exponent of m plus n. What does this mean? When we're multiplying powers of the same base, right? So when I say power of the same base, I'm talking about the whole exponent thing. The base and the exponent, we consider it as a power, right? Or an index. And then when we're multiplying them and the bases are the same, the rule is we add the exponents. Obviously, the opposite of multiply will be divide, and the opposite of addition will be subtraction. So meaning, when we are then dividing powers of the same base, what we then do is subtract the exponents. We also have another law that says if an exponent is raised to another exponent, the operation between them will be a multiplication. So let's just quickly look at a few examples that have to do with this. So if I say to you, I have 2 to the exponent of 3 multiplied by 2 to the exponent of 2. This will be the same as 2 to the exponent of 3 plus 2, which will then give me 2 to the exponent of 5. And according to the calculator, this will definitely be 32. Now, the opposite of this is the division one, right? So if I'm dividing 2 to the exponent of 3 by 2 to the exponent of 2, here I will then need to subtract. So it becomes 3 minus 2, which is just equals to 2 to the exponent of 1. But mathematically, we know that we hardly write 1. If there's an absence of an exponent, it does not mean 0. It means there's a 1 there that we are not writing. And then the last one will be, if I have 2 to the exponent of 3, all of it raised to 2, this will be the same as 2 to the exponent of 6. I'm going to multiply the two exponents. So what you need to understand here, guys, is the bases need to be the same for you to apply the laws, right? That's the condition. The laws are there, but for them to be active and for you to use them properly, the bases need to be the same. Whether it's multiplication or division, the bases definitely need to be the same. But let's look at some more laws that have to do with exponents. Also, if I have two terms that are a product inside the bracket raised to another exponent, we use the property of numbers, the one that talks about distributing, where we're going to distribute this to all the exponents that are there. So that means, remember I said the absence of an exponent means that it's 1, not necessarily 0. So this is the same as a to the exponent of 1 times m, b to the exponent of 1 multiplied by m. And therefore, it then becomes a to the exponent of m multiplied by b to the exponent of m. The other one is, if it's a division inside the bracket, we also apply the same rule, that I'm going to distribute this to the exponent of the numerator and the exponent of the denominator there, which will then give me a to the exponent of m divided by b to the exponent of m. Now, we also have some definitions. The first definition is a raised to an exponent of 0 is the same as 1. Now, with the 0 specifically, I will write the 0 for you to see that there is a 0 there. So it does not matter what you have. If I open a bracket and I write a whole lot of numbers and variables inside there, close it and raise it to 0, everything that is there is just going to become 1. If I have 1,000,000 raised to 0, it will become 1. 1,000 raised to 0, it will become 1. So it does not matter what the number is. As long as it is raised to an exponent of 0, it will forever be 1. That's one of the definitions that we have. The second definition is a to the exponent of negative n. Remember, when you're solving exponents, there is this note that we normally make: leave your answers with positive exponents. To do that, you're always going to take 1 divided by whatever the term is that you were having. So here it will be 1 over a to the exponent of n. Let's make a typical example. 3 raised to an exponent of 2. If you press your calculator on this, it will give you 1 over 9. But let me show you how that comes about. So it's 1 over 3 squared, and then 3 squared we know is 9, therefore it's 1 over 9, which is the answer that you will then get should you press your calculator with 3 raised to an exponent of negative 2. We also have rational exponents. Remember from the concept of rational numbers, a rational number is a number that can be written in the form of a over b, right? It can be written as a fraction. So meaning, when we say we have rational exponents, we're talking about the exponents that are in the form of a fraction, which is the m over n. And it also has a few laws that we need to look at. A to the exponent of m over n will be the same as the nth root of a to the exponent of m, right? And then the last one will be the nth root of a will be the same as a to the exponent of 1 over n. But we're going to look at some questions to try and see exactly what is it that we are talking about here. So the first question that I have here is simplify the following. Please understand something, because I know you guys are very creative. Miraculously, you will then have an equal sign there, and then you have a 0 on the right-hand side of the equal sign. That's not what you need to do, because it says simplify, and it is an expression. Your equal sign will always be on the left, and then you simplify the expression. When I say simplify, I'm saying to you, make sure that there is no common factor there. Make sure that you use your highest common factor, which is HCF. If I have 27 and 9, 9 is divisible in both numbers. So that's what I mean. Make sure that the exponents are in the simplest form that they can ever be in. Lastly, make sure that your exponents are positive numbers at the end. Those are the conditions of you simplifying. But let's look at exactly what do I mean. So the first one is 81x to the exponent of negative 3, y to the exponent of 4, divided by 16x, y to the exponent of negative 4, right? And then all of this is raised to negative 3 over 4. Remember, we always look at BODMAS, and BODMAS says to us, look at what is inside the bracket before you can go outside the bracket. So that will therefore mean this is going to be the same as 3, right? Because remember, 81 is the same as 9 squared, so this will be the same as 3 to the exponent of 4. That's the very first thing that I'm going to do. And then I will have my x there, minus 3. Remember the rule. If I am dividing and my bases are the same, I must subtract the exponent. So it will be minus 1, and then I will have y. There's a 4 there, it becomes 4 minus, the y at the bottom has a negative 4. And all of this is divided by 2 to the exponent of 4. And then I will then close the bracket because there is something out here which is negative 3 over 4. From there, what do? You simplify what we have inside here. So it therefore becomes 3 to the exponent of 4, x to the exponent of negative 4, y to the exponent of 8, and all of this is divided by 2 to the exponent of 4. And then all of this is raised to negative 3 over 4. Remember, the law says here, you distribute the negative 3 over 4 to everything that is inside the bracket. So I will distribute this. Let me quickly use a different color. I will distribute this to that 4, to that negative 4, to the 8, and to that 4 there. So it will therefore become, which will then be the final answer, 3 to the exponent of negative 3, because 4 multiplied by negative 3 over 4 is just negative 3, multiplied by x to the exponent of positive 3, multiplied by y to the exponent of, this will be 8 times negative 3 over 4, so that's once, that's twice, which will give me negative 6. And all of this is divided by 2 to the exponent of negative 3. But remember the rule, leave your answers in positive exponents. So I'm just going to erase up here so that I have enough space. This will therefore be, I'm just going to write it up here. I hope you guys are following. This is then going to be 2 to the exponent of 3, because if it's a denominator and I make it a numerator, it therefore becomes a positive exponent. My x will remain with the 3 there, and then my y must be a denominator because it has a negative exponent, 3 to the 3, and then y to the 6. And then you can simplify that. 2 to the exponent of 3 is 8, 3 to the exponent of 3 is 27, so it can just be 8 over 27, and with those variables there. Remember, the law that I just applied here was we distributed the exponent outside there to the exponent inside. We also changed this and wrote it as prime numbers, right? The goal, by the way, is to always write your bases to be prime numbers. All right, so let's look at this other example here. So what we need here is our bases need to be the same. Remember, that was my condition when I spoke about the laws of exponents, right? And those bases that we are using will be prime numbers at all times. So that's the goal. So let's look at this. This will be 2 to the exponent of x multiplied by 2 to the exponent of 2 multiplied by 3, because 2 to the exponent of 2 is 4 times 3, it gives me that 12. But I must raise all of this to x minus 1 multiplied by 3 to the exponent of 2x. And all of this is divided by 2 multiplied by 3 to the exponent of 3x minus 1, right? And then remember, we distribute the exponent outside to the exponent inside to remove the bracket. So this will then be 2 to the exponent of x times 2 to the exponent of 2x minus 2 times 3 to the exponent of x minus 1 times 3 to the exponent of 2x. And then all of this is divided by 2 to the exponent of 3x minus 1 times 3 to the exponent of 3x minus 1. Then from here, guys, this is where you then look at your laws of exponents, right? We said when we are dividing and the bases are the same, we subtract the exponents. When we are multiplying and the bases are the same, we add the exponents. So you will start with the multiplication one at the top, the multiplication one at the bottom, and then go into the division because it will be a numerator and a denominator from there. So let's look at it. So the first one here, it's 2 to the x and 2 to the exponent of 2x minus 2. The x plus 2x will be 3x. I'm then going to subtract the 3x at the bottom there, which will give me 0. The minus 2 minus minus 1 will be minus 2 plus 1, right? So it means now I'm left with 2 to the exponent of minus 1. And then the 3, it will be the x plus the 2x. It gives me 3x. And then that 3x, I subtract the 3x at the bottom there, it's 0. Minus 1 minus minus 1 will then give me 3 to the exponent of 0. Then lastly, my answer will just be 1 over 2 multiplied by 1. Let me just include it so you can see where did this 3 to the exponent of 0 went. Now I have the last example here. As we are going to the short break, I want you guys to look at it. Please try it out and try and apply the laws that we've done so far. I hope you've been following me. So this is just a test I'm giving you. But as soon as you are back, I will quickly look at it first just to show you what you're supposed to have done, and then we'll move on to another thing that we need to do. But for now, stay tuned. I'll be back. Hi guys, welcome back from the ad break. So I hope you really did try this out, right? But let's quickly just have a look at it and then we'll continue with our lesson. So what you guys needed to do here is remember the laws that I gave you when we're looking at the rational exponents, right? We said that the first part here will be the same as x to the exponent of 1 over. So firstly, let me remove the 1 over there because my 3 needs to still be there, so it's 3. And because it's a square root, it's 1 over 2, right? And then multiply by, this one here will be x to the exponent of 2 multiplied by 1 over 3. All of this divided by x to the exponent of 1 over 6. And then I'm sure from here you can then see what's happening here. You just apply your laws of exponents. Firstly, distribute the exponents and then apply the multiplication and division laws. So this becomes 3 over 2 multiplied by 2 over 3 divided by x to the exponent of 1 over 6. And then lastly, this will be x to the exponent of 3 over 2 plus 2 over 3 minus 1 over 6. And then you can always find what that answer is, right? But my LCM here will be 6. So it means for this to be 6, I multiply it by 3. So that's 9 plus that 6 there, that 4 I mean. So it will be x to the exponent of 9 plus 4 minus 1 all over 6, which will then be x to the exponent of 9 plus 4 is 13 minus 1, that's 12, divided by 6 will just be 2. And then that will just be my answer there, x squared. That will be the answer, right? So I hope you really did try that out and you are seeing your mistakes and you're seeing what exactly you needed to do there. The goal was to change the surds and make them what we said they will be, which is an exponent that is rational. And then from there, and then apply your laws of exponents, distributing, multiplication, and then division. And from there, you can get your answer. Let's look at some more work that we need to do now. So, remember, this is our concept map. We've looked at all these beautiful concepts that we have here. Now we have what we call surds, right? Remember, I said this is one of the keywords that we are doing. Now, a surd will be an irrational number, excuse me, of the form root of a. Now, the condition for this to be irrational is 1, my a must be greater than 0, so it must be a real number, right? Real positive number, that is. Real number, but the condition is it must be positive. Then number 2, a is not a perfect square. So a must not be a perfect square, because as soon as it becomes a perfect square, it will no longer be an irrational number. It will now be a rational number, right? Remember, root of 4 will be equals to 2. So that's not an irrational number. But root of 3 will then be a decimal of some sort with non-ending decimals there. So some laws of sets that we also have here is, if I am multiplying sets that are the same, the rule is you multiply what is inside the set. But remember, listen to what I'm saying. They must be the same, the sets. So you cannot say the cube root of 2 multiplied by the square root of 3, and then you now want to multiply the 3 and the 2. No. It must be the cube root and the cube root for you to be able to multiply what is inside. It must be the 5th root and the 5th root for you to multiply. That's why I am using n there as my general term. Similarly with division, it must be division of the same roots, right? And then you will be able to divide what is inside there. Similarly with the example that I just made, it can be square root of 2 over maybe the cube root of 3, and then you want to say you are dividing what is inside the exponents. Please do not do that. Inside the surds, I mean, right? So it must be the same radicals. We normally actually call them radicals. So it must be cube root and cube root, then it will be 2 over 3, and all of this will be inside the cube root. This is more or less the same as the laws of exponents, where if I have an exponent outside, I kind of distribute it inside to everything that I have inside the bracket. Some more interesting laws will be if I have the mth root of the nth root, it will be the same as me multiplying those, what root it is, right? So if it was 5 there and 6 here, it will then be 5 multiplied by 6, provided that it's just one term inside there. And then the last one will be if I have the mth root of a, all of it raised to n, it will be the same as the mth root of a to the exponent of n, right? But let's look at typical example and actually see how do we do this. Firstly, here it says simplify the following. I have root of 3 times root of 5. The question you must ask yourself is, are my radicals the same? If your answer is yes, then you can multiply what is inside the radicals. If your answer is no, then look at some other method of solving this. But now, because they are the same, this will be the same as root of 15, right? Then plus, here I will have this as the same as root of 15 multiplied by root of 3. All of this divided by root of 3, right? Why am I writing the one at the top as root of 15 times root of 3? It's because my 45 here can be written as 15 times 3, right? And since both of them are inside the same root, I can then separate them with 1 root each. Remember, it's just the law that we looked at, the very first law of multiplying surds. And therefore, this will be that root 3 and that root 3 will divide each other, and I will have 2 root of 15. Now, please don't make the mistake of thinking this is actually supposed to be root of 30, right? Because that's one of the mistakes that you guys make. You think you can add what is inside there and what is inside there. I think maybe a typical example of this, I can say to you, I have 1 root of 15. I'm adding it to 1 root of 15. How many roots of 15 will I have? 2. You see, therefore it becomes 2 root of 15. So it's the same as 1 apple plus 1 apple. It's 2 apples. It can't be the apple plus the apple and then you get something else there. Please make sure that you understand that clearly, please. Let's look at another example here. So this is an interesting one again. Remember, I said my radicals must be the same for me to apply my laws, right? So this will be the same as the cube root of everything that I have here, 16 over 2, plus what I have here is the fourth root, so it will be 4 outside, and then inside here I will have 2 multiplied by the 8 there. Then remember, 16 divided by 2 is supposed to be 8, and then it means I will have the cube root of just the 8, plus here I will have the fourth root of 16, right? And then normally they say to you without the use of a calculator. So make sure that you do try to master this without using a calculator. This will be the same as 2 to the exponent of 3. That's 8 still, right? Then remember, raised to 1 over 3. Plus, this will be the same as 2 to the exponent of 4, and it will be raised to 1 over 4. Why am I choosing 2 specifically? Is because I said to you, when changing these things to be exponents, your basis must be prime numbers at all times. Don't write your base as a number that is a perfect square or something like that. It must always be your prime numbers, please. So the lowest prime number that 8 has will be 2. The lowest prime number that 16 has will then also be 2. If I had a number that its prime number is 3, then I would use 3, right? So that's why I'm choosing the 2 specifically. Now, to simplify this, 3 multiplied by a third is 1, so I will be left with just the 2 there. And then 4 multiplied by a quarter, it will just be 1 as well, so I will be left with a 2 there, and then my final answer will be 4, right? And then because you guys have these beautiful gadgets of yours, which we call calculators, after working this out, you can always just press the whole thing the way it is, and the answer that it must give you must be 4. If it does not, it means there is something that you did not do right with your working out there. So that's just how you test yourself whether you got it right or not. Another example that I have here is it says simplify the following. So I have the 2 outside there, right? And I have the 2 outside there as well. So this will be the same as 6 to the exponent of 1 over 2, right? And this will be raised to the 2 outside there. Plus, this will be 10 raised to 1 over 2, and then there's a 2 out there. Lastly, this will just be 6 plus 10, which is then 16. Or, if you apply the laws, this will be the same as the square root of 6 squared plus the square root of 10 squared. And then you know 6 squared will be the same as 36 plus 10 squared will be 100. I'm sure by now you know your square roots, guys, for the perfect squares. This will be 6 plus 10, which is definitely 16. And that's where your answer will then come from. Another one will be, remember the first law we looked at, we said we distribute this, even that we distribute it there. So this will be 5 squared. Remember the operation in between there is multiply, and this will be the square root of 3 squared, and then plus this will be the square root of 8 to the exponent of 4. And 5 squared we know is 25, multiplied by square root of 3 squared will be 3, and then plus, so here I will have this the same as raised to an exponent of 1 over 2, so it will just give me 8 squared. And 25 by 3 is supposed to be 75, plus 8 squared will then be 64, and then you can add these numbers. This will just be the 9 there, add these 2, it will be 13, and that becomes my final answer there. Then you can play around with your answers there. Please guys, the goal is to try and firstly look at if I can apply the laws. If not, then just apply the normal way of solving these things, where you multiply it by itself. And then another example, which is quite an interesting one now, will be, will be to firstly change the bases, right? I did say that. So this will be the same as the square root of 2 to the exponent of 4n minus 8. Where do I get that from? Remember, 4 is the same as 2 squared. Then I multiply the 2 by 2n minus 4. And then that's where, my 4n minus 8 comes from. Multiply by 2 to the exponent of 3 into 5 minus 2n. All of this is divided by, this will be 2 to the exponent of 4 into the 6 minus 2n. I'm thinking to just write it so that people can actually see where these things come from. And this will therefore become, so here, because I'm going to raise this to the exponent of 1 over 2, it will then give me 2n minus 4 times 2 to the exponent of 15 minus 6n, and then divided by, this will just be 2 to the exponent of 12 minus 4n. All right, so from here you can then apply your laws of exponents, and by that I mean the 2n, the 6n, and the 4n will then be worked out together. The minus 4, the 15, and the 12 will also be then worked out together. So this will become 2 to the exponent of 2n minus 6n and minus negative 4n, right? And I will just write the whole thing as well, minus 4 plus 15, and then minus the 12. So this will therefore become 2. The 2n minus 6n is minus 4n. The minus and the minus there will give me a positive. Therefore, it's minus 4n plus 4n, which will be 0. Minus 4 plus the 15 will be a positive 11. Then 11 minus the 12 will just be negative 1. Then finally, my answer will be 1 over 2. So guys, as you can see, the goal that we've been trying to do here is always make sure that your exponents are changed, right? Not are changed using the laws of exponents, meaning if it's multiplication, you add, if it's division, you subtract. Also, when you are changing your powers, make sure that the bases are in the form of prime numbers. Why I'm saying this is because let's say, for example, we have 12, right? 12 is the same as 4 times 3. But if I write it as 4 times 3, I also need to go again and add another step of changing the 4 to be a 2. So I can just go straight to saying 2 squared times 3 and then continue from there. So always make sure that you change your bases to be prime numbers. Guys, from me to you, I want you to please take a walk a bit around the house, drink some water, and freshen up, and we'll be back with some more. guys, welcome to the last segment of our lesson for today. So we've been looking at some rational exponents, the laws of exponents, the definitions, the laws of surds. Now we need to look at equations, right? Everything we've done thus far has been expressions. Now we're going to look at some equations and try to see exactly what are the principles that we need to apply there and exactly how do we then go about solving them, right? But let's just look at it. Remember, this has been our concept map of everything that we're looking at in this lesson. Exponential equations will be equations that are having the variable as the exponent, right? So it will be an equation in which the variable is the exponent. For example, 3 to the exponent of x is equals to 9. This is an equation. Why? Because my unknown is the exponent. That's why it's called the exponential equations. Now, when we're solving exponential equations, what we need to understand here is we always need to make sure that our bases are the same. Why? Because the law says when the bases are the same, the exponents must also be equal, right? So, for example, with the example that I wrote in the previous slide would be 3 to the exponent of x equals 9. Here you can change the 9 to be 3 squared. Because it's 3 to the exponent of x is equals to 3 to the exponent of 2. Whatever that x is, it must make sure that the relationship of them being equal holds. Hence, the x will just be equal to 2. That's why then the exponents become equal when the bases are equal. Also, when solving exponential equations, make sure you apply the laws of exponents. The example I have here is 9 to the exponent of x minus 1 equal to 27 to the exponent of x, right? So I can change this quickly to be 3 to the exponent of 2 into x minus 1. This will be equals to, this will be the same as 3 to the exponent of x, right? What law am I applying here? I must distribute that in there. So it becomes 3 to the exponent of 2x minus 2 equal to 3 to the exponent of 3x. Remember my previous law that I just spoke about now? If my bases are the same, then my exponents definitely need to be equal. So this will be 2x minus 2 equal to 3x, and this will be 2x plus 3 minus 3x, that is. So this will be minus the 3x because I am adding the additive inverse on both sides. And this will be equals to a positive 2, so it's minus x equal to 2. Therefore, my x equal negative 2, because remember, x must always be positive. So you also need to be able to apply some laws of exponents there. Now, when we have some surd equations, right? We have 3 principles that are very important. I need you guys to please look at these and write them down. If the expression root of a has to be real, it must be that the value of a is greater or equal to 0. If a is less than 0, then the expression will be non-real, right? What does that mean? Remember, a number greater than 0, I know you are thinking about it, can be 4. Right? If I have root of 4, this is a real number because I can find it on the calculator and it will give me 2. But as soon as I have square root of negative 4, this will not be, it will not give me a real solution. It will be a non-real solution. And if we had time, we'd investigate this further into being imaginary numbers that we normally talk about, some non-real numbers, but that's not part of our curriculum as yet. So principle 2 will be square root of a cannot be equal to a negative number since a is greater or equal to 0. What does that mean? I can't have square root of x is equals to negative 2. This is a lie, right? Why? Because the value of x must always be a value greater than 0. So square root of x will then be, let's say x is 2. It means this will be an answer that is positive at all times. Square root of 6, it will be an answer that is positive. Square root of 9, it will be an answer that is positive. So there is no way that it will ever be a negative answer. The last principle, this one you know, square root of a squared is the same, the square root of a, all of it squared, is the same as a. If you look at the previous rules that we're looking at, we said this is the same as square root of a squared, and then you know square root and that 2 there will be half multiplied by 2, which is just a. But let's look at some examples, guys, so that we put this into context. Here, you know, for you to solve this, the goal is to make sure that the surd is on its own, right? At all times. When dealing with surd equations, you must make sure that the root or the radical is on its own on one side, so that you can then square root both sides, so that you can square both sides, and then it will take out that square root that we have there. But if you want to square it while it still has some things next to it, it will really give you a problem because the radical will still be there in your answer. So make sure that it is always on its own before squaring both sides. And when you're squaring it, we're going to be applying my third principle there. So this will therefore be square root of x minus 1 equal to positive 3. Then I can square this both sides. Squared, and that is squared, so it will give me x minus 1 equal to 9. I'm already adding the 1 in my head. So this will be 9, and then my x will then be equal to 10. That's where the 10 comes from. Now let's go back to our principles, right? I said the root of a cannot be a negative number. So if you look at this, I made it to be equal to a positive number, or rather it is equal to a positive number. But the second example now is the interesting one, right? If I simplify this, it becomes x minus 1 inside the square root equal to negative 3. You don't even need to bother yourself with this. You'll immediately go to no solution, right? Because of principle number 2 that I gave you, that a square root of x minus 1 can never be a negative number, because what is inside the square root must always, and I mean it must always be greater than 0 or equal to 0. Let's look at some more interesting questions. So this will then be, remember, 2 minus 7x equal to negative 2x. Here you can definitely simplify. Let me explain why, right? Because I know someone is going to say, now it's negative 2x. Why are we solving? Because we must just say no solution. Remember, it has an x. It means x can be such that it is a negative number. And then when you multiply it by the 2, it then becomes a positive number. So x can be negative 1. If x is negative 1, negative 2 by negative 1 will be a positive number. X can be negative 5. It will then be a positive 10. You understand? So here we can simplify. Why? Because of the variable. The previous example, we couldn't because it was just a constant. It is saying it is equal to negative 3, which it cannot be. So that's where the difference is here. So I'm going to square both sides, which will then give me squared there. This will be 2 minus 7x equal to 4x squared. And then it becomes 4x squared plus 7x minus 2 equal to 0. I'm just rewriting it properly, right? But where this comes from is it's going to be 0 is equals to, I take everything to one side, so it becomes 4x squared plus the 7x minus 2. So that's why I just wrote it in standard form, so that you are not really confused where that comes from. And then from there, I can then simplify this by factorizing this. And remember, to factorize this, it must be such that I get the middle term, right? So this will be 4x in one bracket, and in another bracket it will be x equal to 0. Because my last term is a negative, it means my two signs must be different in the brackets. Because my middle term is a positive, the bigger factor will get a positive. So this becomes 2, that's 1 there, and that is plus there, and that is minus there. Let me repeat what I just said. Last term is negative, it means my two signs must be different. Middle term is positive, therefore the bigger factor gets a positive. So 4 times 2 is 8. That's the bigger factor. And then if I simplify this, I'm just going to go to the next page here. I said it's 4x minus 1 into x plus 2 equal to 0. And then my x will be equal to 1 over 4. Or my x will be equal to negative 2. Then you need to make sure that you test both these answers to say which one will not work, or both of them will not work, or one of them, right? Or both of them will work. So it's either one does not work, both do not work, or both just work. So remember, on the left-hand side, guys, if we go back here, I said the reason why this is defined is because the value of x can be a negative number. If it's a positive, then this will not be defined, right? So it will be 2 inside the square root minus 7 into 1 over 4. And 7 over 4 is definitely less than the 2 there. Greater than the 2, I mean. So 2 minus a number that is greater than it will then give me a square root that is negative, which is not defined. So you always need to conclude, and then therefore x is equals to negative 2. Some people also prefer to say comma, x cannot be equal to 1 over 4. It's really a choice, because if you already said x must be equal to negative 2, it means the other one does not exist. So it's an either or situation. And then what we've looked at so far is you need to make sure that you learn the laws of exponents, right? When we are multiplying, we add the exponents. When we are dividing, we subtract the exponents. But for us to do that, the bases must be the same. If they are not, then make sure that you convert them. The other thing is our bases, we always need to make sure that they are prime numbers, right? Try by all means to make them to be prime numbers, because then that makes it easier for you to work them out. And then also, please go back and revise how to solve exponential equations by doing what? Making the bases to be the same, base same, right? And then if that is the case, the conclusion will be the exponents are also the same. That's the exponential equations, and that's the main thing there. So far, guys, this is what we've looked at so far. We just did not include this rationalizing there because it's something that I believe you guys can then do. It's just multiplying by the denominator in the form of 1, right? So if the denominator is root 2, you multiply by root 2 over root 2, that's 1, right? So that's what we've looked at. We've looked at our equations, some definitions there, integers because the laws are in the form of integers, and then some rational numbers. Lastly, the concept of radicals or surds. Guys, I hope you enjoyed this more than I did as well, or rather like I did, because I don't think you enjoyed it more than me. I love maths. Anyways, I shall see you guys next time, but from me to you, remember, mathematics is food for the soul. Cheers, everybody.